Hey, welcome to The Explainer. Today, we're going to pull back the curtain on one of the buzziest pieces of tech out there, deep learning. We're going to get rid of all the magic talk and actually look at how a machine learns, for real. Okay, let's get into it.
I mean, seriously, think about it for a second. How does your phone know it's you and unlock with just a glance? Or when you ask your smart speaker to play that one song you can barely remember the name of, how does it just get it? It feels like sorcery, right? Well, it's not. It's a process, and we're about to break it down step by step.
So let's start with the big picture view, the main idea behind all of this deep learning stuff. And you might think it's going to be some super complicated, brain-melting concept, but really, the core of it is, well, it's actually kind of beautiful in its simplicity. It's all about learning from examples.
At its heart, that's all deep learning is. It's a way to teach a computer, a machine, to learn just like we do, from experience. So instead of a programmer sitting down and writing a million lines of code with an if-then rule for every single possible outcome, we build a system that can figure out the rules for itself. This is the engine that drives pretty much all of modern AI.
Okay, so how does a system figure out the rules? That's the big question, isn't it? And to understand that, we need to zoom all the way in. I mean, way, way down to the single fundamental building block of this whole thing. One tiny decision maker, an artificial neuron.
Let's make this super simple. Just imagine this little neuron is a tiny worker we'll call the apple picker. Now this apple picker has one job and one job only, to look at an apple and make a call. Is this a good apple? That's it. It's a simple yes or no.
And our little apple picker has a very simple four-step process. First, it gets its inputs. It looks at the apple's features, its color, its shape, its size. But here's the crucial part. It doesn't treat them all equally. It might have learned from experience that a bright red color is way more important than size for a good apple. So it gives color a higher weight. Then it just adds up that weighted info to get a final score. And if that score crosses a certain threshold, boom, it makes a decision and shouts, yep, that's a good one. Now, obviously, one apple picker by itself isn't going to change the world. The real power, well, it comes from organizing thousands or even millions of these guys into teams, or what we call layers. You have the input layer, which just takes in the raw data, like all the pixels in a photo. Then you have the hidden layers, and this is where the real thinking happens. It's like an assembly line of specialists. One layer of neurons might just look for simple edges. The next layer takes those edges and looks for shapes, like circles or squares. And the layer after that might look for noses and eyes. And finally, you get to the output layer, which takes all that hard work and gives you the final answer. Like, yep, this is a picture of a 9.
Okay, so our army of little apple pickers is assembled and ready to go. Now let's throw an image at it and just see what happens. This process, where the data flows all the way through the network for the very first time to make a guess, that has a name. It's called forward propagation.
All right, don't panic. I know this looks like scary math class stuff, but I promise you, what's actually happening inside each of those little neurons is an idea you already understand. It's basically just a tiny calculator running one simple formula to come up with a score. So let's just translate that math into English. All a neuron does is take each piece of information it gets, multiply by how important it is, that's the weight, and then it just adds all of those up. That's it. At the very end, it adds one last little number called a bias, which is just like a little nudge to help push the final score one way or the other. And that's it. That's the entire calculation.
But here's the kicker. When a network is brand new, all those weights and biases, they're totally random. So its first guess is basically a wild stab in the dark. And you know what? It's almost guaranteed to be wrong, like really wrong. But that's okay, because this moment right here is where the learning actually begins.
To learn, the network first has to know how wrong it was. And that's the job of the cost function. Honestly, the best way to think about it is like a report card. It compares the network's guess to the actual right answer and spits out a single number, a score for wrongness. The whole goal of training is just to get that cost score as low as you possibly can.
So how do we lower that wrongness score? Well, we use this beautiful little algorithm called gradient descent. And this analogy explains it perfectly. Imagine you're standing on the side of a massive valley, but it's completely filled with fog.
You can't see the bottom, but you know that's where you need to go. That's the point of lowest error. So what do? Well, first you feel around with your foot, right? You check the slope right where you are to figure out which way is uphill. Then you take a confident step in the exact opposite direction, downhill. And you just do that again and again and again until you find yourself at the very bottom of the valley.
Now, a crucial part of this is deciding how big those downhill steps should be. We call this the learning rate, and it's a bit of a balancing act. As you can see, if your steps are too big, you might take this giant leap and just sail right over the bottom of the valley, ending up on the other side even higher up. But if your steps are too small, you're just shuffling your feet, and it's going to take you forever to get to your goal. So finding that Goldilocks, just right learning rate is a huge part of training a network efficiently.
Okay, so this raises a huge question, right? Gradient descent tells us which way is downhill for the whole network. But in a system with maybe millions of these little weights, how on earth does it know which specific one to tweak? How does it figure out who to blame for the mistake?
And the answer, once again, comes from some calculus that looks pretty intimidating. This is called the chain rule. But I want you to ignore the symbols for a second and just focus on the idea, because the concept behind this is something we all do. It's just about creating a chain of cause and effect, tracing a problem back to its source.
So, in plain English, this process, which we call backpropagation, is really just a super organized blame game. It's brilliant. The algorithm starts at the very end with the final mistake, and then it works its way backward through the network, layer by layer from the end to the beginning. And as it goes, it calculates exactly how much blame each individual weight should get for that final error. That blame is the gradient. That's the slope that tells us exactly which way is downhill for every single weight in the network.
All right, we have all the individual pieces on the board. So for this last section, let's put it all together. Let's look at the full, complete training loop in action, plus a couple extra little tools that help make it all happen.
Okay, one last critical piece of the puzzle is the activation function. This is the little guy inside the neuron that makes the final decision after the score is calculated. This table shows the big three. Sigmoid and tang were the old-school choices. They're good at squashing numbers into a neat range, but they had this major flaw called the vanishing gradient problem, where that blame signal we just talked about gets weaker and weaker as it goes backward, basically vanishing before it can do its job. So now the modern workhorse is ReLU. It's super simple. If an input's positive, it passes it on. If it's negative, it's zero. It's fast and effective, but you got to watch out for the dying ReLU problem, where a neuron can just get stuck on zero and stop learning completely.
And here it is. This is the whole shebang. The entire learning cycle boiled down to 4 steps that just repeat thousands, maybe millions of times. Step 1, a forward pass to make a guess. Step 2, the cost function to see how wrong that guess was. Step 3, backpropagation to play the blame game and figure out who was responsible. And Step 4, gradient descent to nudge every single one of those weights in the right direction to do better next time. That's it. That's the loop. And with every cycle, the machine gets a little bit smarter.
So there you have it. We've stripped away the curtain of magic, and we've seen the elegant, surprisingly simple process underneath. It all starts with one tiny neuron deciding if an apple is good, and it scales up to a massive network that can learn from its own mistakes. The process is clear, so I guess the only real question left is, what incredible, world-changing problems should we teach them to solve next?